All right. Next math concept is to learn the force equation. The equation goes along with Newton's second law of motion. The equation is F equals m times a. F is the force that's applied to the object. Typically, it's a net force. M is the mass of the object, and a is its acceleration. Force will be measured in newtons, mass will be measured in kilograms, and acceleration will be measured in meters per second squared. These are required units. If your acceleration is not in meters per second squared, you would not get newtons for your force. If your mass were not in kilograms, you would not get newtons for your force. If you're given force in newtons, it will calculate mass in kilograms, etc. These are the units that you have to have. If you do not have these units, you need to convert to these units. And for example, if I gave you the mass in grams, you would have to use what you know about metric conversions to convert that into kilograms before you could do the calculation. If I gave you kilometers per hour, you'd have to convert that to meters per second squared for the acceleration part of it. So again, make sure all of those units are exactly the way you see them on the board. If they're not, this equation will not work. Before I get into the math, I want to show you that this is the relationship between force, mass, and acceleration. If I were to rearrange that equation so it says A equals, I would have to divide both sides by m. And I would end up with A equals F over m. In that equation, we can see that force and acceleration are directly proportional. If the force were to double while the mass stayed the same, the acceleration would also double. So if this were 2 over 1 equals 2, if I double this to 4, 4 over 1 equals 4. Doubling the force would result in doubling the acceleration. This equation also shows us that mass and acceleration are inversely proportional. It's on the bottom. If I double the number on the bottom, I will cut the acceleration in half. So if this were 4 over 1, 4 over 1 equals 4. If this is 4 over 2, I double this number. My acceleration would be cut in half. It would be 2. So this equation is the mathematical expression of the relationships between force, mass, and acceleration, and can be used to prove the point, to prove that doubling force would double the acceleration, doubling mass would cut the acceleration in half. Let's get on to the math. For the math, we have to be able to apply the same old problem-solving process that we've always used. First thing we're going to have to do is figure out what these numbers are, the 50 newtons and the 6.7 kilograms. As I mentioned just a few minutes ago, newtons would be a measure of force. And it does tell us that of 50 Newton force. Kilograms are our unit for mass. We're trying to find the acceleration. Our unknown is A. So we've identified our givens, and we've identified our unknown. Now, just like before, there could be hidden numbers in problems like these. For example, if the object is falling, then the acceleration is 9.81 meters per second squared. So we still have some of those hidden things in this. You could be calculating the acceleration of the object before you do the force equation. Again, there's all kind of ways to complicate this up. The equation is F equals ma. We're going to substitute 50 newtons equals 6.7 kilograms times A. Now, in a problem like this, writing in the units, newtons, and kilograms isn't really that essential because you're not going to see the unit cancellation take place with the unit newtons here. 1 newton is equal to 1 kilogram meter per second squared. If you use that unit, then you could actually see the cancellation occur and recognize what's really going on here as far as the units are concerned. But when you're just doing this with newtons and kilograms, it's not going to be evident what's going on. Since it's 6.7 times A, we would divide both sides by 6.7 kilograms to solve this. Over here, everything cancels out and we get A equals. Over here, the kilograms cancel out and we're left with meters per second squared. Again, if you break down the newtons into kilograms meters per second squared, you can actually see what's going on in terms of unit cancellation. But if you just use newtons there, you wouldn't be able to see it. So again, probably no point in writing it in. Just know, if this is newtons and that's kilograms, you're going to get meters per second squared for acceleration because that's the unit I told you you'll get. It's a 7.5. So again, you can go through this and use 1 Newton equals 1 kilogram meters per second squared if you want to see how the units cancel out, how they play out, and see where this meters per second squared really comes from. Or you can just know, since I had newtons and I had kilograms, I'm going to get meters per second squared for my acceleration unit. I would classify that as a relatively simple problem because there's no conversions to do in that. There's no multiple steps to do in that. It's just a straight up force equation problem. This one takes it up a little level. We have a mass of 250 grams, so M is 250. And it accelerates at a rate of 9.5 meters per second squared, so that's A. What is the force? We're looking for N. So we have everything we need to solve this problem with one tiny issue, and that is the unit that's on my map. The unit there is grams, and we have to have kilograms. So we go to our metric conversions. King Henry died by drinking chocolate milk. Kilo, hectodeca, base, deci, centi, milli. We're starting at grams. Our original measurement is in grams. That is a base unit, so we're starting there. We need it to be in kilograms, which is there. We will move that decimal point 1, 2, 3 places over to the left. So move that decimal point, which will be at the end since there isn't one. 1, 2, 3 places over to the left. And you get 0.25 kilograms. Once you've done that, then it becomes a relatively straightforward problem. Force equals mass times acceleration. We don't know the force. The mass we're going to use is 0.25 kilograms. And again, whether you put the unit in here or not, doesn't really matter as long as these are what they're supposed to be, because we know if these are what they're supposed to be, that'll be newtons in the end. And we're going to multiply that by 9.5 meters per second squared. So 0.25 times 9.5 is 2.375. We'll call it 2.4 kilograms times meters per second squared. Kilograms times meters over second squared, that would be newtons. So again, if you understand this concept that 1 Newton equals 1 kilogram meters per second squared, you can see I'm going to get kilograms times meters on the top. I'm going to get second squared on the bottom. That's a Newton. Again, the other way you know that is because these are what they're supposed to be. The mass is in kilograms, the acceleration is in meters per second squared. So you know your force is going to end up being in newtons. This problem, again, takes it up to another level. As I mentioned when I started, the force in this equation is typically a net force, and it's not out of the realm for me to ask you to find a net force first and then use the equation to calculate something. So in this case, a student pushes on a box with a force of 125 newtons. There's a force of friction between the box and the ground of 70 newtons. If the box has a mass of 20 kilograms, what's the acceleration of the box? So we've got two forces here. The 125, that's the applied force. And we have the 70 newtons, that's friction. And we know the mass of the box is 20 kilograms. We're looking for it. Now we have two forces, but there's only room for one force in our equation, and that force is net force. What you need to know is that friction is always going to act opposite of your applied force. So if this student had been pushing to the right, friction would be to the left. These two are always opposite of each other. So to get the net force, we will subtract these two. So we do 125 minus 70, and our net force is 55 newtons. So you just added another twist. You would have to know what's going on with net force to be able to figure out what the net force is before you can do this calculation. And again, once you've done that, then you're good to go. So F equals ma, the net force is 55 newtons, which again is kilograms meters per second squared. The mass is 20 kilograms times A. So divide both sides by 20 kilograms. A is the only thing left over there. 50 divided by 20, or 55 divided by 20 is 2.75. Kilograms cancel, and all I'm left with is meters per second squared. And again, you could do all this unit cancellation stuff using kilograms, meters per second squared as the newtons. Or just know, because this is the unit I need it to be in, and that's the unit I need it to be in, that's going to be in meters per second squared. We can further complicate this. When you got such a simple equation as this one, we have to do other things to make it a little more challenging. We can go straight with a free body diagram and have you calculate the acceleration of the box. Force you to do all that vector stuff, force you to do the Pythagorean theorem. I can even throw in a vector at an angle and force you to break that down into components. We can throw anything that we've done before into one of these problems. If this were the case, the first thing we're going to have to do is to find that net force. We have to go through all those vectors and figure out what the net force is going to be. So in the horizontal, I've got 15 over here and I've got 8 over here. That is when I subtract the two. Going to leave me with a force of 7 newtons to the right. So I got a force of 7 newtons to the right. My upside of this adds up to 32. My downside of this is 9. So I'm going to subtract those two, and I'm going to get an upward force of 23. My net force is the hypotenuse of that triangle. Again, make sure you're attaching these two vectors tip to tail. Where the first vector ends is where the second vector starts. So this upward part goes over here. Finding my hypotenuse is Pythagorean theorem. 7 squared plus 23 squared equals c squared. 7 squared plus 23 squared is 578. Square root both sides. And we get 24. And that is then the force that we'll use in our calculation. The force is 24 newtons. The mass of my box is written in the box. We are looking for A, acceleration. And that's really the way this equation is used most of the time. Most of the time you're solving for A. F equals ma, 24 kilograms meters per second squared equals 35 kilograms times A, divide both sides by 35 kilograms. Third verse, same as the first. But A over here. Kilograms cancel over here. 24 divided by 35 is 0.685. So we'll call that 0.69. Kilograms cancel. All we got is meters per second squared. Again, there's lots of things we can do to make these problems more challenging. One thing that I didn't actually type into this that is a very legitimate possibility that just came to mind is a situation where you'd have to calculate the acceleration. Toy car. Accelerates from, 2 meters per second to 7 meters per second in 3.1 seconds. If the car has a mass of 0.75 kilograms, how much force was applied to it? Again, our first step in this problem is to go through and figure out what all these numbers are, what everything that's in that equation means. And there's a lot there. There's a lot that we have to sort through. So first thing I see there are my two velocities. I have 2 meters per second and 7 meters per second. From 2 meters per second tells me that that is VI. 7 meters per second squared tells me that's VF. I have a 3.1 seconds, that is a time. And I have a kilogram number there, that's the mass. I am looking for force. So that's a long list of stuff, and I know I need to find force. And the only equation I have right now with force in it is F equals ma. So I know I'm going to need the mass of the object, which I already have, and I'm going to need the acceleration in order to calculate that force. I don't have acceleration, but I have all the information I need to get it. I have a VF, I have a VI, and I have a T. I know delta V equals VF minus VI. So delta V is equal to 5 meters per second. Again, VF minus VI. And again, I know acceleration is delta V over delta T, the change in velocity over the change in time. So 5 meters per second over 3.1 seconds. So 5 divided by 3.1 is 1.6. And that'd be meters per second divided by seconds, or meters per second squared. So now I have an acceleration. I use all that information to get my acceleration. A piece of information that's missing, what I need to use F equals m times a. And once I've got that, then I can get to it. I can actually solve my problem. So force equals mass times acceleration. The mass of my object is 0.75 kilograms. The acceleration of my object is 1.6 meters per second squared. .75 times 1.6 is 1.2. And that's kilograms meters per second squared, which is newtons. And there you have it. Like I said, simple looking equation doesn't mean that it's going to be easy. This is physics, and physics involves multi-step problems, always going back to old equations that we used, using those free body diagrams, all that stuff. So, hey, welcome to physics.